This is William Tomos Edwards from Bright Studies, and today I want to show you my solution to this integral that Integrals for You on Instagram recently posted, because based on the comments, people find this integral challenging, and I've got that red arrow pointing at the reason why. Why is this so challenging? Because it's not just the derivative of arctan. We're taking the derivative of arctan and squaring it. So what to do in that situation? The derivative of arctan squared, what do we do? Well, this is the key insight. Whenever you have a situation where you have the derivative of an inverse trig function, but you also have a function where you can use trigonometric substitution, this is a very convenient situation to take advantage of. So first, we're going to go down here and basically reorganize this as the derivative of arctan times the derivative of arctan. That's the great thing about how we can express this. So we can factor that out. We can factor out the derivative of arctan like that. And this is where we can go from here. So the fact is that we can talk about how this function is defined in terms of a right angle triangle. You've got the angle theta. Let's say that side has the length 1. That side is x. And this side has the length of x squared plus 1. Okay, true enough. So, given that, if that side is length x squared plus 1, well then, what we can say is we can say that the value of cosine for this function is 1 over the square root of x squared plus 1. That equals the cosine of theta in this case, right? And so then we can go from there and say, okay, fair enough. Well, then what about this? 1 over 1 plus x squared equals the cosine squared of theta. And you can see where I'm going with this. You can see what it is that I want to do. So from here, you can go here and say, great, this is the integral of cosine squared. Cosine squared of what? Question we got to ask is, where is theta coming from? Right? Where's theta coming from in this case? Well, it's easy. Theta comes from the arctan of x. Beautiful. Theta comes from the arctan of x in that case. It's just x over 1. Perfect. So in this case, incredibly, what we can say is this one right here is equal to this one right here. Incredible. So further to that, what we can do is we can have 1 over 1 plus x squared, right? That's what we can do dx. Incredible way we can just maintain equivalence. And so now where we can go from here is we're set up for u-substitution. So this is a situation that will come up where we can define, we can take a function and just in terms of mapping it to a right angle triangle, we can restructure it and redefine it as a function of arctan. We're multiplying by the derivative of arctan. So perfect, right? We've got the derivative of arctan right here. That's your u-substitution right there. So we go from there. This is just simply the integral of the cosine squared of u du. Awesome. So the cosine squared of u is almost like a common integral. So from here on out, it becomes much more of a plug and chug operation. We use the trig identity to rewrite that. And so we've got the answer. Awesome. So that would be my style for solving that problem. It comes very recommended to practice with these trigonometric substitutions because they can save the day like this and make what looks like a real tough integral very simple. Just turn it into a simple plug and chug operation. Easy.